Okay, welcome back. So, on the last video of this series, we are seeing. Um, let's talk about the last two videos that I have been released for this series. So, I think um, two videos ago we are seeing we were revising about determinant inverse of a matrix, how to calculate inverse of a matrix. So we were on the appendix A of the book. So we revised how to calculate um, the determinant of a matrix 3 by 3. We saw how to calculate um, the inverse of a 3 by 3 matrix. And on the last video, we are seeing how to calculate an inverse of a rotation matrix. So we are still on the chapter 2, and I keep repeating this. I think the chapter 2 of this book is one of the longest, and is good. It's fully of information. Is a good introduction to robotics, and I think, as I said, is the entry for kinematics. Yes, I think is we start on this chapter to see kinematics directly and inverse kinematic of robots. So on the last video, we saw this example, how to calculate inverse of a rotation matrix. So we calculate the determinant, and I said we are focusing on robotics context. So we did a quickly revision, and I passed to you this algorithm. But you can see this by yourself, and I think is very quick to revise this part of matrices. And we calculate the minors, and with the minors we assemble the adjoint matrix, and to calculate the inverse of a 3 by 3 matrix of a rotation matrix, we need to assemble the adjoint matrix and divide this adjoint matrix by its determinant. So this is what we did, and on the end of the video, I said to you that all this procedure, which is very laborious, we doesn't need to do this, because from the theory, now we know that a inverse of a rotation matrix, and only for rotation matrix, I'm not saying this for a commonly 3 by 3 or 4 by 4 or even larger matrices. What I'm going to say again is valid. We can calculate the inverse of a rotation matrix just by transposing. So if we transpose the original matrix of the rotation matrix, we obtain its inverse, and this is valid only for simple rotation matrix. And also said to you that we have rotation matrix from the reference system fx, fy, fxyz, and fnoa, and we can have rotation matrix based on these two uh, reference system. So we can we can have a rotation matrix with the transformation occurring on both at the same time on both systems, and if this situation is happening, this 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 concept is not applicable. So we can verify that inverse of a rotation matrix of a simple rotation matrix, we can calculate its inverse just by doing the transposed function. And I also said that it's important to always take care with the notation. It's a good practice. And it's what I write right here. See, to calculate the inverse of a rotation matrix, we just need to transpose it, the original. And I said that we will do the exercise 2.13 on this video, and is what we are about to do it. So let's get into it. So the example 2.13, is to calculate the matrix representing the rotation around the axis x with 40 degrees. Calculate the inverse of this rotation matrix. But before we solve this example, um, I'm going to read some steps before this example. I'm going to take a step back to pass to you some concepts that the book brings, and I think is important. I'm pretty much sure that is important. So I'm just going to read what the book says. One thing that I didn't tell to you is that these simple rotation matrices, which can also be a rotation matrix around the axis y and the axis z, they are called unitary matrices. A unitary matrix. It happens that all rotation matrices are unitary, then all we need to do to calculate its inverse is just transpose it these matrices, and we have to pay attention that only the simple only the rotation matrices are unitary. So for a translation matrix, this is not valid. It's not a unitary matrix. And the analogy that we have to do is that a unitary matrix, which is a rotation matrix, is the matrix that we can calculate its inverse just by doing the transposed function. And as I said, if this matrix is not a simple matrix, so if it's not a matrix that is doing a transformation related just for one referential, reference system, not referential, reference system, it can be a simple rotation matrix, and one thing leads to another, and it's not a simple, so it's not unitary, so we cannot calculate its inverse just by doing the function of transpose it. And that's all we need to know at this moment. And I'm saying this, I take a step back to pass that to you, because this example that we are about to solve is a example with a matrix of order 4. It's a 4 by 4 matrix, and now we will see that for a homogeneous transformation matrix of 4 by 4 of order 4, it can be demonstrated that the inverse of this matrix can be right and dividing this matrix in two parts. The part of rotation can be simply transposed because it's unitary, and the part of position of this homogeneous matrix is the negative of the scalar products of the vector P for each one of the vectors NO and A, as followed. So it's before this example. So it's a characteristic generic 4 by 4 matrix of transformation, and now we'll call this terms or element. I will not call entry because we are not representing numbers, and I'm not sure if that makes sense exactly. For me it does. So you can call right now this as term or element. So is nx, ny, nz, and you will see that we add this fourth line, which is the scale factor that we add to keep this matrix on its quadratic form. And we already saw that it's more easy and to calculate the inverse, to do operations with a quadratic matrix is OX, OY, OZ, AX, AY, AZ, and the vector. Sorry. And this is the scale factor W, scale factor. Okay, and let me again draw the reference system. So is Z, X, and Y, and link it on the origin of this reference system. We have other reference system, which is the NOA. Right here is NOA. These are reference systems. And let me see something. Reference system is different from framework. And let's see the difference. Right here, we have this reference system or coordinate system, as you can see, and it also saying that is a global frame or fixed frame, but I'm calling reference system. And in the factor, this link we call as frames. Okay, so keep that in mind. Reference system is different framework. Right here, it's not referential, is reference frames. Reference frame. This U I think we can call um, reference system. But right here, the the robot, on the origin of the robot, we call reference frame. The hand of the robot is a reference frame. The end effector is a reference frame, and right here again a reference system that we can write equations to describe the motion of this robot, the motion of the links, the motion of the whole system based on this reference system. And we have coordinates, so we can say that this part or this part is doing a transformation based on the universe reference. Okay, let's get back. Let me put this a bit down. So we have our reference system f, x, y, z, f, n, o, a, and I forget to draw the vector p on the origin of this reference system. So let's draw with the color yellow the vector p. And if you remember, we have restriction equations for this point on the space is n. Let's do, let me draw the reference system F and O separately. Is N, O, A, and these vectors are perpendicular between each other. Okay. So n scalar product with O is equal 0, and scalar product with A is equal 0, and this because they are perpendicular. We have A perpendicular scalar product with O, which is equal 0, and they are unitary vectors. So the length we can take by calculating his magnitude, and the length of all these vectors are one unitary vectors. Now, if we want to calculate the transpose matrix, um, we just need to swap the lines by the columns, and in this, um, just for the rotation part, as I said on the beginning of this explication, and the part of the position given by the vector is the negative scalar product of the vector p with each of these vectors in OA. So the beginning of this explication, it was, as the book says, for a homogeneous transformation matrix of order 4, it can be demonstrated that its inverse matrix can be dividing the matrix in two parts. The rotation part can be transposed, and the second part, the part of position, is the negative scalar product between the vector p and each of these vectors in OA. So let's swap. Let me write this. First, the first part, we divide in two parts. Divide in two parts. One is the rotation part, rotation. And for the rotation, we do the function of transpose. So we transpose this first part, transpose it, this first part. The second part is the position. And for this, we calculate the negative product of P with each of these vectors this way. So let's write the transposed matrix of this matrix. So we just need to swap this line by this column. So is nx, nx, ox, ax, and 0. Right here, swapping the line by the column is ny, oy, ay, and 0. Right here, nx, nz, oz, az, and 0. And this is for the rotation part. And for rotation, to calculate its inverse, we just need to transpose it. And for the position part given by the vector, we do the scalar product of the vector p with each of these unitary vectors in OA. So it's the negative product between the vector p with each one of these vectors. Okay, so now um, we are ready to solve this example 2.13. So right now we have to remember what is it a rotation, what is the characteristic rotation of a matrix, of a rotation matrix around the axis x. So what is it, the characteristic matrix of a rotation matrix around the axis x? So rot of x with a given theta angle, the characteristic matrix of this rotation matrix is 1, 0, 0, 0, cosine of theta, sine of theta is 0, minus sine of theta, cosine of theta. And this we saw a few videos ago, a few lectures ago. And the cosine of 40 degrees is equal to 0.766. The sine of 40 degrees is equal to 0.643. And now if let's make this smaller so it doesn't take too much space. I think it's okay. Let me copy and paste right below. And now we have the values of these terms, elements, and okay, so is the cosine of 40 0. 0.766, sine of theta 0.643, and minus sine of theta minus 0.643, and cosine of 40, sorry, 0.766. And we cannot forget of the scale factor. Add the scale factor on the fourth line to keep this matrix on its quadratic form, so we can calculate its inverse. Okay. This way. Now, to calculate the matrix representing uh, the inverse of the rotation matrix around the axis x with 40 degrees of with 40 degrees. So to solve this, we just need to swap the lines by the columns. And if we calculate, let me bring this, uh, let me drag this, copy this, and paste below. Because if we calculate the scalar product, in this column is representing the vector, and if we calculate the scalar product of the vector p with each one of these unitary vectors, its scalar product will result in 0, as the position of the vector, we kind of don't have a vector, because these are the coordinates of the vector. So if they are 0, we don't have any vector. We don't have coordinates for the axis y, don't have coordinates for the axis z, we don't have coordinates for the axis x. So we can represent p this way, and we do not have coordinates px, py, pz, so we don't have a vector. So the scalar product is 0. And to calculate the inverse of this rotation matrix around the axis x with a theta angle of 40, we'll just transpose the rotation part. So let me copy this. Right here is 40. We have already calculated. Pretty simple. Is cosine of 40, sine of 40, and the inverse of this matrix. We will swap the lines by the columns. And if you do this, we will see that we are left with the following matrix. Okay? Right now, let's solve the example 2.14. So it asked to us to calculate the inverse of the given transformation matrix. So the given transformation matrix is that one. Zero point 0.5, 0.866, 0, 0, 0, 1, 0, 0.866 minus 0.45, 0, 0, 3, 2, 5, and 1. Um, let's copy this. To use as reference for our solution, and copy the procedure that we have to follow to be succeed our on our resolution. So we need to transpose the rotation part and calculate the negative scalar product between the vector P and the unitary vectors NO and A, and this column it points to us the position of the vector of the point. So we have a vector linked on the origin of our reference system, and on the end of this vector we have it's given by these coordinates. So we have the length, so let's do this. Let's transpose the rotation part so we will swap the lines by the columns. 0, 0.866, Now this line 0.8660 minus 0.5. Now this line 0, 1, 0, and now calculating the negative product of the vector p with each of these unitary vectors. So we just need to take this reference, minus 3 times let me copy this so I can see better what I'm doing. Is the negative product, so minus 3 times n, which is 0.5, plus 2 which is the other coordinate of this vector p, so it's 2 times now ny, which is 0.866 plus the other coordinate of the vector p, 5 times and now nz, which is equal 0. And on the second line, minus the coordinate of the vector times, right now is 0, plus 2 times 0 again, plus 5 times 1, minus 3 times 0.866 plus 2 times minus 0.5 plus 5 times 0. Okay. And calculating this, rewrite this matrix. Sorry. Minus 3.23 minus 5 minus 1.589 and adding the scale factor, so we keep this matrix on its quadratic form. And also for other benefits, and we obtain this matrix, which is the inverse. Don't forget that is the superscript. Superscript. Sorry. And I think it's all for now. And if we do, if we calculate the original, if we do the product between the original and its inverse, we will obtain the identity. Um, that that that's too much work. So I'm just going to set them side by side. Okay, and for now that's all. And on the next video we will solve more examples. And that's it. Thank you.